So I want to find the dimensions of the rectangle of largest area that can be inscribed in that region and the positive x and y axes. So what we're looking for is a rectangle like this, some sort of thing like this, or maybe a rectangle, like this. Anyway, the corner of that rectangle needs to lie on that line. And so what we can say is that the dimension or the coordinates of this guy are x comma, and then I can solve this equation for y, move it over here, and I'll say y is equal to 1 minus x. So x comma 1 minus x. So that's the coordinate of that rectangle. So what I want to do here is I want to find a rectangle of largest area. So in other words, I want to maximize the area. So in order to do that, the first thing I need is I need a function that gives me the area. And so the area function, a of x, is going to be the height of the rectangle times the width of the rectangle. So it's going to be x times 1 minus x. So that's my area function. I can multiply that out, and I get x minus x squared. And then I want to maximize that. Of a of x. So I need to find a prime of x, 1 minus 2x, and set that equal to 0. And so I can subtract the 1 over, divide by the negative 2. So x is 1/2. This is a critical point. Okay, and if I look at my a prime to the left and right of 1/2, if I look to the right of 1/2, I plug in 1, say. Well, let's plug in, if x is 1, then it's 0. Okay, so let's plug in like 0.75. So a prime of 0.75 is going to be what? 1 minus 2 times 0.75 is negative 0.5. And so that's negative. And if I plug in like 0.25, so I'll have 1 minus 2 times 0.25, I get something positive. So by the first derivative test, I have increasing, then decreasing. I could also do the second derivative test and see that a double prime of x is negative 2. So I know my function a of x is concave down. I also know that a of x is concave down because it's an upside down parabola. So I know it's going to have a maximum. And so the x coordinate is 1/2, and the y coordinate that goes with that equals 1 minus 1/2, which is 1/2. And so the coordinates of the point, the dimensions of the rectangle are 1/2 by 1/2. I'm going to evaluate each of the following integrals here. So the first one, I'm looking at this one and I see kind of an inside function and an outside function. And so I know probably I want to do a u substitution on this. I'm thinking about letting u be equal to x squared plus 5. So usually you want to let u be equal to whatever the inside function is. And then my du will be 2x. So I almost have my du. So what I can do is I can rewrite this integral here. And I can multiply a 2 in here and a 1/2 out here. And so what that will give me is this will be my du. That will be my du. And this here is my u, and my u is raised to the negative 1/2. so now I'm ready to do my substitution. So I have 1/2 integral of u to the -1/2 du. And so then I can integrate that. I can find an antiderivative for that by adding 1 to the exponent and dividing by new power. So I'll have u to the 1/2 times 2 over 1 plus c. And so I end up getting 1/2 times 2 over 1 is 1. So I get u to the 1/2. And what is u? U is x squared plus 5 to the 1/2 plus c. For this one, I want to find an antiderivative, and I want an antiderivative of e to the 5x, so it's going to be 1/5 e to the 5x, and I want to evaluate that from -2 to 3. If you didn't know that it needed to be 1/5, actually let me start over and I'll explain why that 1/5 is there. So again, we'll do a u substitution. We'll let u equal 5x, and then du is 5 dx. And so again, what I want to do is I'm going to multiply a 5 in here and a 1/5 out here. And so then I can see that's my du, and that's my e to the u. So I'm going to have 1/5 times the integral of e to the u du. And note that my bounds here, over here, these bounds are x values, but I want my bounds to be made into u values. So if x is equal to 3, what's u? So if x is 3, I'm going to plug x in here. So if x is 3, u is 5 times 3, and so u is 15 here. And if x is -2, I can plug that also in here. So 5 times -2 is -10. And so I don't need to go back to x's anymore. I could just do everything in terms of u from now on. And so I can go ahead and complete this. I have 1/5 e to the u, and I want to evaluate that from -10 to 15. And so I can plug those values in. And that's my answer. For this one, it looks almost like a fundamental theorem of calculus part 2, except what I see in my bound, instead of just a plain x, I have an x squared. And so when I evaluate this, I'm going to have to use the chain rule. So just the derivative of the outside part is going to be, so let's just go back and review the fundamental theorem of calculus part 2. It says that the derivative with respect to x, the integral from a to x of f of t dt is equal to f of x. Okay, and so this here goes in there. Okay, so I can go ahead and write this as x squared plus 2. So this is going in here for t. X squared is going in for t, and then I need to multiply by, from the chain rule, I need to multiply by the derivative of the inside function. My inside function is x squared, so I multiply that by 2x. And that is my derivative.